So, let me first briefly introduce a little bit about the project. Okay. So the term project, the term project. So you will okay, let me turn off the lights. So the term project, you will have a team. Okay, maximum you can have 2 students to organize the team. Okay, you have and any topics related to the field of reinforcement learning, then you can work on. And the documents you need to submit are the one A4 page proposal. So you can write more than A4 one page. So like this proposal need to include topic, problem to solve, motivation, and plan. Okay. Then after that, at the end of the semester, you need to submit one term project report. Now I will provide a format. Okay. So here, how many of you have used the LaTeX? LaTeX 1, 2. It's overlap online the LaTeX, like academic paper writing, the environment. Okay, 2 students. So I will provide both LaTeX format and the Word format, so you can write the term project report. Okay, slides for presentation, and the source code with documentation. Documentation means that you need to have a manual and some code explanation. So so each team need to present their term project at the last lecture, which is December 15th. And the proposal submission day is November 3rd, Friday, which will be, yeah, after the midterm, okay? The first week of November, next month, after the midterm. And the submission is December 13th, which is Wednesday, okay? The last week of this semester. So I already attached this template here in the iCanvas, then you can download. So it's a Word file, MS Word file, then you can fill out before the deadline, you submit your proposal. Any topic you are interested, you want to work on in this semester. So also in this template, so let me just download. Okay. So I already provide this template. So you need the topic you put here, okay, replace with your topic, and your team member, the name and student ID, name, student ID, problem description, background and motivation, plan with schedule weekly. So I give each section, I give the instructions, what kind of contents you need to write. For example, the problem description, what is the major problem you are trying to solve in this topic? So it should have a reasonable size to be done within 7 to 8 weeks, okay? Background and motivation, where is the problem from? Why is it worth solving? And any applications in some areas, existing solutions, what kind of solution they are already been used for solving this problem. Plan with schedule. So what kind of plan you're gonna have weekly? So I put the table here. You can write down actual contents, the sequence and the week. So from 1 to 1. Okay, the starting time is October 23rd. Okay, it's a midterm. Yeah, midterm week, I guess. Okay, and then you have a working item. You can write down them. So you can remove replace all the blue colored contents before submission. Okay, so blue colored contents you need to fill out by yourself. Okay, this is the term project proposal. And after submission the proposal, I will provide the format for the term project report and also slides format. Okay. Yeah. Any questions? Okay. So this is for the the project report package submission. So you need to submit the report, slides, and the source code with menu, with documentation. Okay, so we will talk later. Then homework. Okay. So in the homework, I provided two iPad notebook file here. So each one, the first one you would deal with the multi-armed bandit problem. The second one you deal with the DP problem. Okay. And for example, I just click and download one. But how you can once you download in your download, so I download here, right? The file homework 1-1. Then you can open the Colab. Okay. So here Colab. Then you can click the last one, upload, browse from your downloads. Okay. Then the first one, open. Then will be uploaded to your Colab. Okay, once you upload it to your Colab, you'll see some instruction, what kind of instruction and how to run, and the contents, where you need to fill the code. Okay. For example, here you need to implement this incremental average based on in the equation we derived from the Bellman equation, right? This, so you need to write down your code. Later, others like here, argmax. The function of argmax is to select an action that maximize the value, right? So you need to, so the difference, actually NumPy also has argmax, but the difference is that NumPy's argmax choose the first, if you have a time, then they just choose the first one. But in our case, you need to break the tie. Okay. So means randomly, you need to add some random number for the same value, then randomly select one. So it's a little bit different. So eventually you can use the NumPy argmax. And now after that, you need to implement the greedy agent for the multi-arm bandit problem. Okay. So you need to input your code after this is the place. Okay, which is up in this function, update estimate. After that, you need to improve your code. There's some, so, oops. So yeah, so basically you can check the slides or textbook. There is the update estimate, the algorithm. So you can write down your code here. Next one is now we run 10-arm bandit experiment. So based on the code, the agent, greedy algorithm. So we build the greedy algorithm, the agent here, and the environment. Then we run. If you finish correctly, you finish the previous functions. Then if you run it, you will see some output here. So it will print out all the environment information, and each step it run where each step. So with each step, it will show some data, each arm's expected return. Okay. So this is the first, okay. This is the first one. And the next one is that we want to run like experiment, long-term experiment to see what is the performance of different, like basically we have two methods, right? Greedy and the epsilon greedy. So in this case, we just first try the greedy agent and we just run. You will see some result here. After that, you need to implement this epsilon greedy algorithm. Epsilon greedy algorithm inside of this epsilon greedy agent class. What you need to do is that to implement this get action function, okay? Your tasks is shown here. The major function you need to implement is based on this epsilon greedy action selection. It's also in the algorithm in the textbook. We show the simple bandit algorithm. So you need to implement this part. So since you need to use argmax you developed previously and input the action value here and check the probability. Okay, here. If you correctly finish this part, then you can run. The remaining is also 10-armed bandit. Run this epsilon greedy agent. It will run, show you some data and information. Eventually, we output, print out the expected return, okay, for each arm. So eventually, we come to this particular experiment that we want to check what is the influence of epsilon. So we try to vary the epsilon from smaller to a larger or larger to smaller number and to see what is the curve there for the expected return. Actually, if you finish the above the function, then you can just run remaining. You will get some data. So initially, we first test the experiment code with 10-armed bandits and with the fixed epsilon value, which is 0.1, and you will see some curve. After that, we vary the epsilon from 0.0 to 0.4. So as you can see here, you will see the different performance. So you probably can find the best performance among them. So it's like a hyperparameter. Yeah. Then if you run correctly implemented previous code, you will have some results here. Okay. This is the first programming. The second one is so similarly, we upload here again. Upload the notebook, browse. The second one, which is here. The second one is a little bit, so actually the bootstrapping codes are from the textbook. But the thing is, in the textbook, they only implement the value, the policy iteration. So we also need to do the improvement, okay? So the code is from the basic code is from the textbook, okay? Now, your task is to implement the policy improvement part inside of policy iteration in chapter 4.3 on page 30 in the textbook. So basically, we already have this the set value function, how to compute. So basically here, we are using the Bayerman equation, okay, which is located here. The Bayerman equation is stated here. Reward plus discount times the state value, okay? Then we just update, then draw the image. So if you run it, you will see okay, yeah. So let me, okay, let me run it. Okay, the first one, the second one. So the compute, now draw the figure is to visualize, to plot. Then the first figure, we'll use the previous one to draw a grid word for us, and we'll show you the state values. So now here the draw image policy actually is same to the previous one, draw image function. So actually we don't run it. Now what you need to implement is here compute policy improvement IMP. Okay, you input your code here. Actually you can refer to the page 80 of the textbook, or in the slides we also have this policy iteration process and how to draw the figure. So okay, so if you run the bootstrapping code, you will see this the converge stable state values. Okay, all those are the state values calculated based on those settings. Then what you need to do is that you will generate another grid word. Then each this box will have a policy. You have a left, up, right, down policy. So use the arrow to represent. And for the arrow symbol, I already put here. Okay, the arrow symbol is put here. Arrow symbol. So left arrow, up arrow, right arrow, down arrow. Then yeah, you can based on the action state value to update the policy. Yeah, this is the second homework. Second homework is more freedom to implement. So you can, yeah. So you need to design the process to draw the figure. Okay. Yeah, any questions? Okay. So the deadline, you will have 3 weeks to finish this homework. You need to submit until October 29th, after the midterm. Okay. So this is for the homework. Yeah. Now let's go back to our lecture. So outline for today, we're gonna review the DP and MC. So in the last lecture, we finished the end of the MC Monte Carlo methods. So in the important sampling, so we will review from the beginning and reach that part. Then after that, we will learn the temporal difference learning, in short, TD learning. So in TD learning, we have a lot of subtopics we can use. Okay. So as usual, we have this IR framework. So we have this usually the agent has a brain. The brain is a policy pi. Then usually we try to improve this policy step by step, right? Then for this policy, we have the state value function and action value function. State value function, we use VS to represent. Action value function, we use QSA. So here we have a action A to represent the action. Then Q means quality of this action. Okay. So previously in DP, we already derived the Bellman equation and Bellman optimality equation to describe how we can improve the state value and action value. Okay, there is a theoretical background here. Now, with this iterative ways, then we can update. So evaluate the policy, then update the Q quality, then improve the policy. So we can evaluate and improve, evaluate, improve. Eventually, the policy will reach to the stable, and which is proved to be the optimal. Okay. Then the overall objective is that through this process, actually, we maximize the expected return, because if you maximize the expected return, it will show, it means that we are getting the optimal solution. So a recap, dynamic DP in the IR, dynamic programming IR. So dynamic DP is just used Bellman equation to evaluate the policy. Then we designed the iterative policy iteration. And DP, we also use the Bellman optimality equation to improve the policy, which is policy improvement. And after that, we use the value iteration because simplify the process, we just, once the value is updated, we just greedily select the maximum value, then which is the optimal policy. Now later we generalize the policy iteration process, those the circle, okay? So this GPI, we're gonna use this concept again and again throughout this lecture because this is kind of general pattern to design IL algorithms. Later we move to this Monte Carlo method. So the motivation of using MC method is that if we don't have a complete knowledge of an environment, means that we don't have the dynamics of the environment, how we can do. So Monte Carlo methods is the kind of methods that we can sample sequence of state action and reward from actual or simulated interaction with the environment. So it doesn't need the model of the environment. It doesn't need the knowledge of the environment. It just evaluates the environment based on experience continuously. So similar to the multi-arm bandit problem, but multi-arm bandit problem, so each arm doesn't have the state. We just have action. It will have the return. There's no state. But here, MC has the multiple state for each arm, then bandit has some interrelated. So yeah, the key idea here for the MC prediction. So now we are here in the prediction. So from now on, when we talk about the prediction, means that we want to evaluate the state values. Okay. Then later on, when we talk about the control, means that we want to control the policy based on the state value and based on the action value function to improve the policy. So here, when we talk about the prediction, MC prediction means that we want to evaluate the state value function. So the key idea is that we just average the return observed after visit to a state. So the formula is that by given a set of episodes. So you have a lot of place, and each place we evaluate the average returns. Then through enough episodes, then we can converge. So each state will be converted to a stable value. Okay. For that case, we designed our first algorithm called first visit MC prediction. Okay, the first visit means that we only check so we generate a sequence based on the policy pi. Then we generate the sequence. So this is one episode, right? So here we loop forever. So for each episode means that every time we generate a new episode by following the policy pi. So this episode, until the end termination, then we trace back of this episode, then collect the rewards we get, okay? Accumulate the rewards and calculate the average. So this is what we learned in the last lecture. So for example, the example is here. So if we have a state S0, S1, S2, then we have two episodes. So S0 is shown, was visited in the episode 1. We got the return G as 0. Then you got average because in the second episode, the S0 wasn't visited. So we just average by 1. But for S2, it was visited twice in both episodes. So we need to average by 2. So this is a simple example how this algorithm works. So this is another description. So last time we calculate this for the first visit, right? So for example, here we have now we want to calculate the state value of A. So A in the episode 1, we visited 3 times, 1, 2, 3. So for these 3 times, but we only count, since we are considering first visit, so we only count the first visit of A, which is here. So now we just trace back of all the value back to the first visit 3, and we calculate from, so -3 plus 4, -4 plus 2, and 3. So we calculate together the first episode, the state value A is 2. The second one, similarly, A happens here. Then we just trace back, add them together, sum them together. -3 plus 3, -3 plus 3 equals 0. So we add both the value, 2 episodes value together, divide by 2, because we count twice, the first one and the second one. So eventually we got the VA equals 1. This is the average, the return, right, for VA. We can also calculate VB. We did in the last lecture. So we compare the DP and the MC. So the DP is that we consider all the possibilities of surrounding state, of next state, and update the state value. So because we have the model of the environment, so we can use the model of the environment, the dynamics, the transition probability, to update. But in MC, we don't have those model, we don't have those transition probability. Then we can also update the state value based on experience, based on the multiple episodes, E1, E2, E3, so multiple episodes continuously. Then every time we update, then once for example, we update the state value from the episode 1, then the state value episode 1 will be used to the next E2, again update. Then after E2, then the state value will be moved to V3, then again update. Eventually we'll convert to the stable value, okay? So now previously it was the prediction, Monte Carlo prediction, to evaluate the state value function. Now we want to estimate the action values, because the selecting action is more important here, because we are updating our state value based on the experience, based on the action, right? So that's why but the thing is we need to select every actions. So that's why we need to have this so-called exploring stars. Now, if you want to update the policy, then we want to choose the better action. So it means that actually we need to try every action, right? Because if you don't try some actions, you don't know whether that action is better than others, even though you have the existing knowledge of the current action or policy. So that's why we have these two assumptions. If we want to improve based on MC, we need to have these two assumptions. The first one is the exploring stars. The second one is the infinite episodes. So the second one is it's like a flexible condition assumption, because we can run this simulation or this in large enough times, then we can kind of consider it as infinite. But the first assumption is a little bit strong. Exploring stars means that we need to use every action to see what is the feedback or return, okay? So if we have this ES, exploring star, with the MC method, so we use a similar name, which is called epsilon greedy policy, okay? So we just randomly select, so they have each action will be chosen randomly with a little bit probability. Then we update the policy based on this Q, the action value function, right? Then that is the action that maximize the Q. Then update the policy pi. So in this case, so actually we need to assign a small probability to every action. But sometimes it is difficult to do so, because, for example, you consider the autonomous driving vehicles, they have this continuous state. So actually the states is super huge. The actions is super huge. So you have a continuous actions. So you need to, if you want to assign small probability to each actions, that is a very heavy work, and also for the machine, it's difficult to choose those actions. So that's why we have the epsilon soft policy. So in this case, actually we slightly altered the probability for the non-greedy action and the greedy action based on the available action size here. So actually we average the probability for that particular state. Yeah, the size of the action we can have. So also at the same time, we have this on policy, off policy concept. What is on policy and what is off policy? So on policy is that we work on the current policy, then improve it again and again. Off policy means that we will use or evaluate another policy that is analogs to the original policy, but the new policy will do the exploring, and with the data, then we can update the original policy, make it close to the optimal. So this is the MC, MC control without ES. So compare the two methods, the epsilon greedy and epsilon soft. So yeah, this is how it looks like in the algorithm. Now this is on policy first visit MC. It's like yeah, the epsilon soft policy, right? This the algorithm. So we put this action selection based on some probability, the probability here. Okay, if it's not greedy action, then we put assign the equal probability to those non-greedy action. If it is a greedy action, then we use the opposite side, 1 minus epsilon plus the average the probability for each non-greedy actions. Eventually, we come to this off-policy prediction where importance sampling. So in the last lecture, we stopped at this importance sampling, and I enriched the contents about this importance sampling to make it easier to understand. So basically, previously when we considered the on-policy prediction or control, is that we have this dilemma that we need to update the optimal policy, but at the same time, we need to choose different actions, right? Different behavior. We need to explore different possibilities. But in that case, actually, the efficiency become low because you need to try different actions, and some action may bring a better result, some action may bring worse result. Now so if you have a worse result, then your return value will be adjusted lower. Then later on, you need to update it again. So there's some like a fluctuation. Another approach is to use two policies. We call it off-policy methods, right? So we call it the one method, the policy is for learning become the optimal policy. We call it the target policy. We use VS, so original the VS to represent the state value function. Then the other one for exploring to generate the behavior called behavior policy, we use BS to represent. Oh, is this red? This is, we should pi s, right? Not the VS. Actually here, this should be pi s because this is a policy, right? Here it should be pi, not V, okay? Pi s and BS. So we call this type of approach of policy learning. And one important technique to do so is to use importance sampling. Importance sampling is a general technique that we can estimate the expected value under a different distribution, okay? So let's look at the original, the importance sampling. What is the meaning? So you see here we have a sample. So we have a sample. So the B is a distribution, the like behavior distribution. Now we can draw a sample, a set of samples from the B. So X represents the sample from the distribution B. Now we want, based on this sample, we want to estimate the expectation of X based on policy pi. What we can do is that we use the definition of the expectation. We write the expectation. So x times pi x. So this is a definition, right? Now we just times bx divided by bx. So it's a redundant value. Then we switch the position, then put to the bx out and move the bx to the below the pi x. So now we define this pi x divided by bx as rho x. So we call this rho x as the importance sampling ratio. Okay, so you see here, actually we derive this expectation of random variable x based on pi, and then we move it to estimate it based on the bx, which is another distribution, but we just give a ratio to adjust the variables scale. Okay, so if you now we just put this rho x to here, you see if you look at this shape, it's if look at the original definition of the expectation. So actually we just put x rho x as the random variable. So actually what we are doing is that this is exactly definition of the expectation of this x rho x based on the policy B, the expectation of this x rho x based on policy B, right? So now actually we got this relation. We have this, if we want to evaluate the expectation of a random variable x based on policy pi, actually we can evaluate the policy B with this rho x ratio together times the original random variable. So because the expectation of a random variable can be approximately to be calculated as this to get the average. So 1 divided by n, sum all these contents xi rho xi. So this is approximately, it's just average, right? To check the average. Then the xi follows the distribution B, which is here. So it's just, now we can calculate the expectation random variable x based on policy pi, based on the samples from B. So yeah, this is the concept, the foundation of importance sampling. So eventually you can write in this way. So you can calculate the E pi x equals the average of the xi rho xi. So this rho xi is called importance sampling ratio. Then we will use it in our approach of policy, the MC method. Okay, so as an example, so assume that we have these two distribution. Each distribution has 4 values, like 1, 2, 3, 4, and each random variable. So like they have this probability distribution. So that if you sum them, they equals 1, right? So the complete probability distribution, Bx, Rx. So then now our goal is that our target is to evaluate the expectation of pi x. So we don't know the pi x itself. So even though it's shown here, actually we don't know it. What we can do is that we just give input, it gives some output. We don't know this itself, okay? So the actual expectation of the result is 2.2, it's here, right? It's 2.2 here. So this is the goal we want to reach. We want to evaluate, get close to this 2.2. But we only get the sample, we only get the sample from the Bx. What we can do is that we first just randomly select a variable, a sample from the Bx. For example, x equals 1, we just select the 1. Then the Bx, the probability of Bx, is x equals 1 equals 0.85 based on here, right? Now we put this 1 into this x, so it should be like a list. Now at the same time, we input this x equals 1 into this pi x. We got the 0.3, which is here, right? 30%. Now we have these 3 value, 1, 2, 3. With these 3 value, we can calculate the first result of importance sampling based on the equation, the approximation we derived in the previous one. So what we do is that we use x times the ratio between these two values, pi x divided by bx, which is 0.3 divided by 0.85. If you calculate, it will equal to 0.835. Now this is the first estimate of the random variable x based on positive pi. If you link this one, you will see here, this is the first estimate, the first estimation of the random variable pi. It will be located here. It's a little bit far, kind of far from the actual value. Then we continuously do the process. The next one, we randomly sample with a random variable from this bx. For example, x equals 3. In this time, the bx equals 0.05, which is 5%, right? Then we put this 3 to here. So now x actually includes both 1 and 3 because we need to use all the data, the random history random variables together to calculate. Then at the same time, we also input the x equals 3 to this pi x, which gives 0.1, which is here, right? 10%, 0.1. Now with this, we can calculate this expectation of x under the policy pi, which is now you remember we need to sum all this value, right? The first one is, so remember x equals, so include the history data, so 1 and 0.3 divided by 0.85, which is from the previous drawing. And the second one is the x equals 3, which is here, and times the pi x divided by bx, which is 0.1 divided by 0.05. So all the number n actually here is 2 because we have 2 samples here, 1 and 3 divided by 2. This time we got the average value is the 3.18. If you look at here, now it's kind of the second estimate of this EX under policy pi is 3.18. Now we can do another one. So this is the third time we randomly select based on bx. This time we get the x equals 1. The same, the bx equals 0.85. Then we put this this sample into this list. And the same, similarly, the pi x equals 0.3. Then we can calculate again. So all the first two items are the same to the previous one. And then we add one more, which is 1 times 0.3 pi x divided by bx. And so now we sum them together, divided by the total samples we have collected, which is 3. This time we calculate the expectation is 2.24. So actually, after the 3 samples, we are already close to the true value of the EX on the policy pi, right? We got 2.24, which is located here. So if you continuously doing this process, so if large enough, actually eventually you will get very close to this 2.2. So this is the importance sampling process, how it works. Okay, actually importance sampling technique is widely used in different machine learning and AI areas. Okay, in different areas we use these importance sampling techniques. Original purpose of this IS is that you try to check every possibilities. Okay. Yeah. Any questions? Okay. So now we move to this. Based on this knowledge, then we move to our reinforcement learning in MC, Monte Carlo methods. We use the importance sampling. So now, because you remember we have 2 policies. The first policy is the original policy, pi s. The new policy is BS, okay, which is BS here. So now the thing is what we can do is that previously we just averaged the return through the one episode. then update the state value. Now we can just put this row importance sampling ratio to here to rescale the return from the BS, the distribution, the behavior policy, right? BS means that even though this episode is generated from the BS, but we use this row to rescale it back to the original policy pi s. And that we call this row is the same name, importance sampling ratio. So now the remaining stuff is just derive the importance sampling ratio. Okay, so assume that we have this a sequence, the AT, we select the action AT, then we got the next state, we select another action, next state, and here we reach the termination state. Okay, so then what's the probability of this particular sequence? So you can generate, based on one policy, you can generate numerous sequence, right? So for a particular sequence, what is the probability? So this is the probability of this particular sequence based on the ST with an action following policy pi. So we can, because this follows the Markov property, then we can divide them into multiple chunks, multiple parts. So we have a policy. The policy decides the action, the probability of the action, right? Times the state transition. We times them. So this is the probability for the takes the first action and move to the next state. And we continuously divide this. Then we select an action times the transition probability. Continuously, we reach to the termination state. So we like make a product of all of them together, which is here pi ak under sk times p sk plus 1 under sk and ak. So they just have the same form. So then we just time all of them from the starting time to the termination time. Okay, the two step. So this is the first deviation. So you got this. So remember here we are checking this probability based on pi. So we can similarly we can also you remember we have this BS, behavior policy. Then we can generate the trajectory, the sequence, the state action trajectory based on the BS, right? So you will now later this one will become B, okay, instead of pi. So even though they have they follow different distribution, so now we will use the importance sampling to calculate this ratio. Then even though we don't know the pi, then we can scale back to the pi. So here it is what I'm talking about, right? So we just generate the two sequence, like calculate the probability of sequence based on policy pi and policy b. We put them together, divided them, then pi ak sk b ak sk. So they are using the same environment. The transition probability is the same, so they can be canceled out. So eventually we have this ratio. This is an importance sampling ratio, which is similar to the previous one, the one we derived here, right? Pi x bx, importance sampling ratio. But the thing is here we just put them into this reinforcement learning stuff, Monte Carlo method, okay? Then this is the importance sampling in the MC method. So now we want to use this importance sampling ratio to update, to estimate the policy pi. Even though we can use the policy B to explore the environment. Okay, here, so the return of the behavior policy B is equals this one, right? Expectation, the GT is the return, then equals the state value function, state value of policy B. Even though because it follows the policy B, the distribution is different. It does not reflect showing the original, the expected return of the target policy pi. So we use this ratio to transform it, rescale it, and it will change back to the original, get close to the policy pi we just time this rho t to t minus 1. Just is because it's just it's a range, right? It's accumulated the ratio, so it's a range. Now for deriving the eventually the importance sampling, so we have some settings. So you look at carefully here. We define this the set of all time steps, okay? So in which the state S is visited, denoted by the TS, so the special TS. So if you look at here, if you look at S1, the example is here, for the state S1, it was visited T1, T3, T4. T1, so these are time steps. The S1, state S1 is visited. So in T1, in this time step, we move to the S1. So just check the state has been visited. So in this setting, we have two kind of methods. One is the every visit method. Another one is the first visit method. We have been seeing this before, right? So actually now we just consider the every visit. We also denote the TT. T here, capital T means the termination, the terminal state, okay? Capital T is the terminal state T, means that the time step of termination is the first time of termination following time T. T is so T can be randomly kind of starting point, okay? Any starting point. We also denote the GT, the return after T, absolute TT, capital TT. So it's like if you look at here, I draw this small timeline for you. So the setting is here. We have a starting T, then termination T. The GT is the accumulated rewards return, okay, for this episode 1. So we may have another episode 2. We also start from the T, then termination T, okay? So the GT, this is a GT in E1. Could be another GT in E2 for a particular state. So this is setting we are here, okay? So now the GT set belongs, so it's like the return set belongs to the state S. Then the rho T, the rho is the ratio, the IS ratio, right? So with this, we put this ratio before the GT to rescale the return from the policy B. So now actually our purpose is to estimate the V pi S. So the pi, we use the distribution of behavior policy B to estimate the V pi, okay? So this is, we call it ordinary importance sampling. So the difference is that, so previously we just average it. So to make a mean of the return. So you see here, the divided by this time step is visited, right? How many times is visited, the size of the time step is visited, then we just get the average. So, but now we times the rho T. Okay, we will look at the comparison between this importance sampling and the previous one, the first visit. Okay, so we call it ordinary importance sampling. You just simply add this scale, the ratio, to rescale the GT. Okay, remember this rho is the product of the two policies samples. Okay, the pi and the B is a product of a series of this ratio. Okay, we can also, if we can give the weight. So based on the scales, this importance sampling ratio, the summation, the sum value, then we can put the weighted value for each GT. So that we just change this from previous, the size of the state has been visited to the sum of the importance sampling ratio, means that actually the importance sampling ratio has been weighted. The ratio has been weighted for all the summation of the rho T. So if you expand this, you will see how it looks like. But initially, when you look at this like this fraction is a little bit confusing, right? So we have this sum symbol. So we need to sum all the time step. So this rho t to t, capital T. So actually this one is a range, okay? It will include all this important sampling ratio and rescale this GT, okay? So until here, okay, there are two variables, GT and times rho t, and divided by this part, rho t to here. So, but actually, if you look at here, you may consider that why we don't cancel this one. Actually, we cannot, because this one is times GT and do the summation. This one is just sum all the rho t. Okay, if you expand this VS, you will see the detailed the process. So you consider this is a sequence, okay? So from the time 0 until termination, so each time you have a return, then you times this important sampling ratio until to the last one. So actually the last one, you just have a one ratio of from the pi divided by b, okay? So this rho t to t minus 1 equals this product of all the rows along the trajectory. Yeah, a little bit. So we will look at the example later, how it works. So yeah, so we have learned this. We first look at this on policy every visit MC prediction. So even though we are looking at the off policy, but this we're gonna update this on policy to the off policy. Okay, so we have this on policy every visit MC prediction. In the previous lecture, also I mentioned that we check this first visit, but this time we use the every visit. Okay, every visit is just removed the one condition to check whether this is the first time or it has been visited or not. So every visit, we will check all those state visits. Okay, so the difference is that a policy pi is here. We need to evaluate the policy pi. So instead of, so the other process are the same. Instead of generate an episode following pi, we generate the policy following policy B, okay? Even though B is known policy, is a distribution of this policy is known. The distribution of policy B means that the action, the probability of each action for a particular state, okay, is B. Now we generate this episode based on the policy B, behavior policy B, okay, which not the pi. Remember, we are designing an off policy, means that we're gonna have two policies. Original policy is pi, the new policy is B, behavior policy, okay? B is here. Now we just update. So now because we are following another policy, we can update the name, which is off policy now. Then we update the weight here, for this return, accumulated return with W. W actually is the product of the important sampling ratio. We will update the W later. Okay, since the initial value of W is 1, because if you look at the sequence here, we generate a sequence from 0 until termination T, capital T. Now when we check each step, actually we do the reversely. We found the second and last step, the step before the termination, T minus 1, capital T minus 1, capital T minus 1 until 0. So we trace back, right? From here, T minus 1, trace back to the beginning of the step. So if you look at here, the first step, the W equals 1, you just add the last reward, RT here, okay? Now we update this W based on the important sampling ratio. Rho T is pi divided by B. So T here is a particular time point. So you see here, W will be the product of multiple row, right? When this loop goes on, when we iterate this loop, iterate all the steps. So the W will be the row, the first one will be row capital T minus 1. Then will be times the row capital T minus 2 continuously until we reach to the 0. So if you continue, so you will see this process. So W0 equals 1, the initial condition. W1 equals row capital T minus 1. W2 equals row T minus 2, T minus row T minus 1. So we just continue this process. Eventually you will reach to the original, the 0. So each W will be an importance sampling ratio for this state, okay? Importance sampling ratio for this state. So this is the important, how we can update the previous on policy MC prediction to the off policy, okay? Now we use this example again to calculate the every visit MC prediction for the VA or VB. Here we have two episodes, same two episodes, but the one difference is that these two episodes are generated from the behavior policy B, okay, which is known to us, which is different from the target policy pi. Now we want to calculate the VA. I use the subscript here 1 to represent the episode 1. To represent the episode 1. Then V subscript 2, we represent the second episode. Okay, so if you look at, so now we are considering the every visit. Okay, every visit means that we need to count, for example, this every visit of state A, we need to count 1, 2, 3, 3 times. Okay, now how we calculated the VA. The first visit will be from, if you trace back from the W0 minus 3 times W0, right? And trace back again, 4 times W1, 4 W2, 2 W3, 3 W4, until the first A. So this is the first A. Then we continue. The second A, the second one is located here. Then the W will be the same. Okay, we'll trace back again. The third A. So each of these value will have the ratio to rescale it. Okay, this is because these episodes, the two episodes are generated from B, not from the pi. We are using W to rescale those returns. Similarly, the second episode is simple because A just happened once. Then we can just write down the minus 3 times W0 and W1 times 3. So plus 3 and minus 3, the rewards. Okay. Then eventually we can calculate the VA equals, sum them together, sum the V1A and the V2A divided by 4, because we counted 4 time visit of state A, right? The first episode has 3 visits. The second episode has only 1 visit. So we counted 4 times, divided by 4. Then we got some value. Because this W, since we didn't specify the pi and B, even though B is known, but we didn't specify the probability here, also pi, we don't have the actual value. But for some system, the pi, so this W0 can be calculated based on the pi and B, okay? Also, I gave what is the implication of each W. W0 equals 1, W1 equals the importance sampling ratio of row T minus 1. So what is the meaning of this? Row T to capital T minus 1 means that product of all the row T along the time step from the time T until termination, okay? So then, so try calculate VB. You can try calculate this VB based on this current setting. So actually, we are looking at the internal mechanism of this MC prediction. So inside of this algorithm, how it works, right? Yeah, can you calculate this VB? Yeah, VB. So we are using the every visit. So you will be having you also need to have a V1B, V2B. Then V1B will be has been visited twice in the first episode. The first one, second one. So you have two lines. The first B, the second B. In episode B, in episode 2, B has been visited twice. You also need to have two lines. They're totally still 4 times. So you will write. So simple, right? The first one will be the similarly minus W03 plus W14 plus minus W24 until here, right? Until here. And the second one, just the last, because the B is the last, before the state before termination, then just minus W03. Then in episode 2, we need to write twice. The minus 2, so W2 times minus 2 plus W1, 3 plus minus W03. Then plus the second one is minus W03. Then we sum the two values together, divided by 4, because B also visited 4 times 2 in each episode, right? This is how you calculate. So this is the internal mechanism, the process of this every visit MC prediction. Okay. Any questions? So now we move to I don't know if we need to take a break or we continue. So just move to the. Okay, let's just yeah. Now we move to this incremental implementation for weighted IS. So previously, when we derive this importance sampling, we have two: ordinary importance sampling and weighted importance sampling. So in this algorithm, we just used the ordinary importance sampling, which is here. We just simply put the weight in front of the G and average them, average all the visits, which is exactly what happens here. We put the weight, the ratio in front of G and average all the visits, the size of visits of the state of one state, right? Now how we can calculate, we use the weighted importance sampling. So what we do is we want to design a similar this algorithm, but since we are designing the algorithm, need to be like an incremental updated, right? How we can incrementally implement this weighted importance sampling. So we use based on the weighted importance sampling, we can rewrite the form. So WK here actually is the row, right? WK is a row. We just use the WK to represent. And previously we used the time step. Now we just use the general term, which is K equals 1 until N minus 1. Previously we used T minus 1, right? So then we just make it general. Then we make it equals Vn, which is the state value for a particular update, right? So with this definition, we can derive to this updated rule, okay, in this shape. Actually, this shape looks similar to us, right? We look at similar one we had before when we designed multi-arm bandit problem. So there's also incremental implementation. So this is the original value, this is step size, then this is the error, the new return minus the current value. This is the error, the adjustment for the current. Then we update the next value, okay? Then Cn here is Cn plus Wn plus 1 is definition, okay? Remember Wn is the importance sampling ratio. So there's a deviation from this part to here, how we can, it's located in the appendix. You can look at, if you click, go to the appendix, you will see. So our goal is that from this weighted importance sampling to the incremental implementation, is similar to the process we did before, how we can do the same. So this is the 2, okay, this is the, we can rewrite 2 here, this is the 2, this is the original, the definition of the 1. What we do is that we first write, based on this definition, we write Vn plus 1, we just change subscript to n plus 1 instead of n. Now the sum of this n minus 1 become n because we add 1 here, right? So you just replace the n minus 1 with n plus 1 minus 1, which is n here. So the ending bound of this sum is changed to n. Now we just extract the last item, Wn, Gn, out of this sum. So now so because the last item has been removed, extracted from this sum, right? Now so look at this form. So we can rewrite this definition. We move this denominator to the left side. So it will become Vn times the sum, then equals the other side, sum Wk, Gk. Look at here, we put this. So this part is equal to this part. Then we just put this right-hand side to replace this location. Okay, we replace this part in 3 as the Vn sum Wk. In this one, so from here to here, we add a subtract Vn Wn. It's like a redundant value, so it doesn't change the original value, right? Plus Vn Wn minus Vn Wn. Now, in this case, we just rearrange the place, put the Vn Wn to the first one. So we extract the Vn, then put the Wn Gn with the last minus Vn Wn, extract the Wn. But in this case, we rearrange the Vn. So you will see Vn becomes times this sum plus the last item Wn, and Wn times Gn minus Vn. So this one is just, we moved it back, just exactly the k to n Wk, right? Then we can simplify to here. Now we can just separate them. So this part will be equals to, so this one will be cancelled for this Vn. So then Vn only has the Vn plus this part, then which is the one Wn divided by the sum of Wk for k from 1 to n times Gn minus Vn. So which is the exact format we are using, the incremental implementation, okay? This is how we derive this, the incremental implementation here, from here to here. So with this format, with this rule, actually we can design the algorithm like step by step to update the value. Okay, so let's take a 15 minutes break and come back. Okay. Okay, let's continue our lecture. So far we have seen this how we can do the incremental implementation of the weighted IS. So from the definition of this weighted importance sampling to this updated rule. Okay, with this rule, we can design an algorithm like gradually updates the state value function, right? State value. Okay, this is the off policy MC prediction. Uh, you you see here we are using this. Okay, we are using this. So if you look at others are the similar, so we look forever each episode. So there is a for any policy with coverage of pi, then to B. So actually we are creating a policy, behavior policy based on pi. But the thing is the policy B need to cover all the actions of pi. Okay, that's the precondition. If so, because we're gonna use the importance sampling ratio to estimate or kind of evaluate the pi. But if the B doesn't have some action, the pi has, no, it cannot evaluate, right? So now we generate the episode following B. Now we are kind of, it's off policy. We generate episode, a sequence, a trajectory based on B. Others are similar, G equals initialized, W equals 1. Now we just use this weighted importance sampling, the incremental implementation. We put this gamma G plus RT plus 1. This is update, accumulates the return, the rewards, right? And we update the C, which is the denominator, serve the denominator of this the updated rule. Now we put here. So this is exactly the equation we derived in the last page. And we updated W. W is a product of different ratio at each time step, right? Different pi and B ratio. So this is how it works, right? It's not, once you get you know how it is derived, then it's not that difficult to understand this part. Yeah. So this is just exactly the implementation of the weighted importance sampling. Okay, so we can, we previously, actually we do the prediction. Prediction is just update the state values. Now with this prediction, actually we can do the control. Now we're gonna use off policy MC to work on the control, how we can improve the policy. So you see the behavior policy has a non-zero probability of selecting all actions, which is the condition I put to here, right? That I highlighted here. This is the condition. B should have cover all the actions that shown in pi. And the behavior policy should be soft, which is the absolute soft policy. Means that we're gonna like divide the greedy and non-greedy actions. So in this case, actually the process is similar. The only difference is that we need to select the maximum greedy way to maximize the action value function by selecting a particular action A, right? That maximizes the Q. Then we put this action to the pi S. So the pi S will be the optimal action at this particular time state, the time step. So all the steps are the same. The only difference is that we add this policy control update. So we select one A, give to the policy pi st. So for this particular state, the A is the best option that maximize the current action value function. So now we update this importance sampling ratio again. Okay, so notice that actually there is a, so previously in the previous, when we look at this here, the importance sampling ratio, previously it was a pi ATST. Now it become 1. Why? Anyone? Because this is the importance sampling ratio, right? So we are updating, we are using the importance sampling ratio to rescale the behavior policy. But here we are using 1 instead of the pi. This is supposed to be the importance sampling, the scale factor. Any idea? Okay, so the why we put 1 here, because the action has been selected, right? It's deterministic. Actually, there's no the probability for the action. The action has been selected, which is argmax A. So put to pi. So the pi now is fixed to a particular action already. So that's why we put 1 here, right? Because we are updating the policy based on the argmax. So greedily update the policy. So once we update the policy, we select the best action. The pi has been fixed deterministic at this state. That's why we just put 1 here. There's no need to put pi. Okay, this is the reason we put 1 here. So now they'll come to this summary of the Monte Carlo method. So from the beginning, the motivation of the Monte Carlo method is that if we don't have the knowledge, a complete knowledge of the environment, how we can do, we observe, we explore this environment based on experience. And through those experience, we update the different states value, okay, with multiple episodes. So we designed our first visit MC prediction. So we only count the first visit of state and update again and again. After that, we work on the control. We try to, once we update those, we get our optimal policy. We want to control our policy, update the policy. There are 2 assumptions we can do the control. The first 2 assumptions, the first assumption is the exploring stars, which we need to give probabilities to every possible actions. We call it epsilon greedy policy. And the infinite episode it can be approximately reached, right? But this ES assumption is too strong. If we don't have this assumption, what we can do, we can use epsilon soft policies, like we divided greedy and non-greedy action and assign different probability to it. We call it epsilon soft policies. Then another method, another approach of doing this is we use the off policy MC prediction and the control together. So that's why we rely on importance sampling. With importance sampling, we designed the ordinary IS and the weighted IS. Okay, with this weighted IS, we also derived the incremental implementation. In this way, we can design the algorithm, gradually update the prediction and improve the control. So this is the summary of the Monte Carlo methods. Okay, as you can see here, we have multiple episodes. So each episode we work on different state value, then we can update the policy. Okay, this is the summary of the Monte Carlo methods. So there's one issue here. Predict the values and control the policy after each the episodes. So if you look at this tree diagram or backup diagram, you see here each episode we need to, when we run the algorithm, when we start each episode from the beginning, we from here to the terminal state, from starting point to the terminal state. So when we can only update those particular state when this episode ends, right? If this episode is very long, so it means that we need to wait until very long episodes, then we can update those different states, right? So if just from efficiency point of view, actually it's not efficient. Actually the convergence time will be longer, will be much longer if the trajectory, the sequence of the episode is very long. So this is the issue of the Monte Carlo method. Okay. To solve this issue, then we move to the new method, which is called temporal difference learning. Okay. So if you look at the name, you will see what is the meaning. Temporal difference learning. Temporal, it means time. So it's like we can update the state value or update the policy once we move to a new state. Then we just check the difference between two time steps. We call it temporal difference learning. Okay, before doing that, let's look at this small demo. They train, I cannot enlarge. Okay. They train this cut pole to make it to the balance here. Okay, it's from the beginning, the trial number 2 at the beginning. So you see here, it fails many times. Okay, this is the second trial, third trial. Then you will last 5 seconds. Initial the first and second trial is like just 1 or 2 seconds. Now it can work on 5 seconds. So like let's say each episode or each step, each training, each round, improve the policy. So the machine, let's say computer or AI, or the policy has been improved. They try different policies, right? How to maintain the balance. After trying many times, eventually it can, hold the balance to keep it. Now it's first success, right? To reach to the balance, but eventually fall down again. Try again. So almost there. Give some external, yeah, it can, yeah, just like 7 times trial, it already can maintain the balance, right? So it's like how we train those different models to reach some goal. Okay. Yeah. Yeah. Now we move to the TD learning. So TD learning is a combination of MC ideas and DP ideas. So what is the ideas we used from MC, DP? In MC, we learn from experience, right? We don't know the knowledge of the environment. And DP is that we know the environment model, then we update our estimate based on the surrounding the states, right? All the possibility we contribute to the current state, we update. So TD learning just use both merits together to do the prediction and the control. Yeah, to do the evaluation, state action evaluation, and the action value function to do the policy update. So we have this circle, like from pi to q. Q here is the policy, the quality of the action. Okay. Now actually the idea is simple, right? So we recall that every visit MC method, we use this format, the the incremental implementation, right? The VS plus alpha GT minus VSC. Alpha is a step size. So previous, if you use the off policy, alpha becomes the W divided by the sum of W. So alpha is like can be different settings. Then GT is a return from T to the termination. GT is a return, right? From time T until the termination. So now the TT method is that instead of using the GT from T to termination, we use the immediate update VS from the next time step, okay, which is here. So this represents the next steps, the return with some discount and the state value. So it's like the state value with some discount and some return from the next step. So from the next step, this kind of the update from next step minus the current state value with some discount. This is the step size. Then we update the current state value. This is simple, right? Just means that we just use the next step, the state value, the reward, and update the current step. So we call this method is TD0 or one-step TD, and the value inside of this rectangle, this bracket is a TD error, and it is a special case of TD lambda or n-step TD algorithm. So we will talk it later in this lecture, maybe in the next week. Yeah. So because TD0, because we just consider one step, so we use 0 to represent the one step. Now, just based on this setting, we can design a new method based on this the TD. So others are the same. So our input is the policy pi to be evaluated. We have this algorithm, step size. So we design this alpha belongs to 0 and 1. Initialize V. So except we give the termination state value equals 0 because we don't care about the terminal state, okay? Then loop through each episode, then loop each step of episode. We just get an action from the pi, then take an action, receive the reward, then move to the new state. So with this information is enough, then we just update the previous step. So if you look at, so this is the formula, the equation we look at previous page, right? If you look at this backup diagram, so we have this state, then you take an action based on the policy pi, you move to the S prime with some reward R, which is here. With this information, we can immediately update the previous step, state value from the value of the state S. Then we can continuously, so now we move to now since we are in the S prime, we move to the next step, then we can immediately update S prime again. Just update step by step. So this is the TD0 method. So if we compare DP, MC, and TD together, we put them together. If you look at here, the DP, the first one is the DP. We just consider we have the state S here. We have a state. Then based on policy pi, we have multiple actions to select. Each action has a probability. If we select a particular action, its So this particular action has this reward, and we move to the new state. We just collect all those possibilities to update the neighboring states, to update the current states. The MC case is that we update a particular state until the end of an episode. Then we move to the new episode. Until the end of this episode, we update the state. Then TD is just combine both. We also consider the next one, the neighboring state. Then we also update immediately to the previous one. So the TD, the features of TD is that no environment dynamics, update state dynamically. So instead of like MC until the end of the termination of the one episode, we can update. So the TD immediately update the previous states. We look at the example from the textbook, travel time estimate in driving home. So this example serves the purpose of understanding this TD. So from the algorithm point of view, it's not that difficult to understand, but if you look at the detail, the process, actually there's some more information to understand. So assume that you are working in your office in the evening, so until the like 6 p.m. you need to leave and you want to drive home. So we design multiple states. You want to leave the leave state and reach the parking lot state, exit highway state, secondary road, the home street, arrive your home. So multiple states. So we have this total predicted time, predicted total time, and predicted time to go. So the difference is that this is total time, this is time remains, and elapsed time, the actual time elapsed. So when you leave the office, then you expect that you will spend 30 minutes to reach your home, right? But when you move to walk to your parking lot to get your car, you feel like, oh, it may take 40 minutes to reach my home. Then gradually, when you drive to the highway and leave the highway, you see, oh, I may spend 35 minutes more to reach my home. The total, because maybe in the highway it's not that heavy traffic, so you feel like you drive faster, then you only need to take 35 minutes. When you exit the highway, you feel like, oh, the traffic it become heavy, then you move back to the original expectation, the estimate, 40 minutes. Then you take 3 minutes to reach the home street. You see eventually you reach home. Actually takes 43 minutes. So 43 minutes is quite far from your initial estimate, right? Similarly, so this time to go is the future time to be spent. Like expect 30 minutes, 35, 15, 10, 3. Then this is the actual time left. From here to here, actually you spend 5 minutes. From parking lot to exit the highway, you spend 15 minutes because this is the total time elapsed, so include the 5 minutes. From exit highway to the secondary road, you spend 10 minutes, right? From secondary road to the home street, spend 10 minutes. And from home street to the arrive, 3 minutes. So the elapsed time, we can see the time spent on each state transition, right? So which can serve as a reward. For example, from leave office to the parking lot, it takes 5 minutes. 5 minutes can be the reward for this from state leave to the state parking lot. 5. Then from 5 to 20 is 15 minutes. 15 can be the reward from parking lots to exit highway. So in this case, then how we can update our estimate for this travel time based on the TD. So if we use MC method, you would see that only when we reach home, we can update our estimate from each state. But for TD, once we reach to a new state, we just immediately update the current estimate. When we reach to a new state, we update our new estimate. So this is what is the major difference between MC and TD0. So for example, here let's calculate how we can update our estimate based on the TD0. So now we want to update this predicted time to go. Roughly we predict 30, 35, 15, 10, 3, 0. So but actually our prediction is not that a little bit far from the actual time span. So we use this TD method, the equation in the TD method. We use the next state to update the current state. So for the first time, when we reach to the parking lot, so the first state is leave, the next state is parking lot. When we reach the parking lot, we have so our reward is 5 because we spent 5 minutes, and plus the gamma, so the gamma is the discount rate, we just consider 1 for simplicity. Then the current state we estimate is 35. Then 5 plus 35 minus the previous state, which is 30. Then this is error, right? Then the TD error. Then we put them together, add that to the previous state. Then what we got is 40. Actually, we updated the previous estimate with 40. So instead of 30 minutes, even just move one step, just we spend one step, we already updated the previous estimation better. Actually, actual time we spent is 43. We already got the better estimate, 40. Then in the next state, when we drive to the highway and leave the highway, exit the highway, then we can steer to, now we are in the highway state. The reward is the 15 minutes. We drive the 15 minutes in the highway. 5 to 20, the reward is 15. The 15 plus the current state we estimate is 15, is the actual experience, right? From the agent. We add them together minus the previous state is the TD error. Then we update the previous state. We add them to the previous state update, which is 30. So we update our estimate to 30. We continue this the process. You can gradually update our estimate, which is 13, 3. And eventually, actually, we get very good at the estimate. So in this way, each step has been updated step by step, right? All the state have at the end of the state, all the state value will be updated accordingly. But if you use MC, only when you reach to the end of the state, you can update those states from the efficiency point of view. So you want to get the better result as soon as possible instead of wait until the last minute, right? So the advantage of TD prediction. So there are multiple advantages. The first one is TD bootstraps the learning like DP. So here we use the bootstrap means that it provides some initial updating or guessing information to the learning, kind of accelerate the learning. No need a model. So this is what we got from the MC, Monte Carlo methods, implemented in an online fully incremental fashion. So previously, when we derived the weighted importance sampling, actually we need to kind of derive some incremental implementation rule for it. But here, the TD naturally is incremental implementation. We don't need to derive some incremental equation for it. It is online because once you move to the next state, we can already update the previous state. Next state, update. Less susceptible from experimental actions. This means that because we want to explore different possibilities, right? We want to try different actions. So those worst actions are actually, we consider them as the experimental actions. So then in the previous MC, we need to run episode from the beginning to the end, then we can update. So through this process, actually, some actions we took are not that good. Actually, we consider those experimental. Then those experimental action actually affects the total estimate of the state value, right? So it means that actually if you use the MC method, when you reach to the end terminal state, when you update those state values or the action values, some of those values actually are affected by those worse and not good actions. There's also proof that it's convert to the optimal value based on the policy pi. Okay, in practice, actually TD methods converge faster than the constant alpha MC methods. Yeah, so because it's online, so you can update dynamically instead of until the end of the episode. Okay, so let's take a look at the an actual example, the random walk. So we have this setting. So it's like a simplified Markov process. So because each state only has two sides, either left or right, let's say two movements. Because here we don't consider action, we call it Markov reward process, no actions. There's only possibility either to left or right at each state. So every time we start this process from the C, then if you look at the reward, so only this part has a positive 1 reward reach to this terminal state. Other reward are 0. Actually, it implies that this terminal state is the desired, the goal we want to reach. So other state we don't want to go there. So if we use the like either DP or like iterative policy prediction, we can get the true value of each state. So which is 1/6, 2/6, 3/6, 4/6, 5/6. So either we use the Bayes equation because we only have like 5 states here. We can just list 5 equations, then solve the system of linear equations, then get this result. Or we can run some program to gradually iterate to this point, right? So this is true value. Now the purpose is that which method has better, faster convergence to this true value. So we run both MC with different step size. Alpha is the step size. You see the comparison. This is root mean square error. So actually it means that it mirrors the state error to the true value we calculated. So you see here MC kind of converge slowly overall, generally, right? Even though we have give different alpha, different step size, so they converge slowly. When they reach to the 100 episode, it's still far from the world, much worse than the TD. So if you look at TD, they kind of reduce the error fast, right? Then with this alpha step size, if you look at here, the alpha equals 0.05, actually reached, even though initially the speed is slow, but eventually reached the better solution, better state. So yeah, this example serves the comparison between TD and MC. Generally, TD is better than MC. Okay. So previously, let's look at this algorithm, TD0 method. So this method is for estimate the state value function. Now we want to not only estimate the state value, we also want to improve the policy, control the policy, right? So that's why we move to this so-called SARSA policy TD control. So the name SARSA is from the state action reward state action, okay? Because this method just use all these the multiple elements together to update the action value function Q, okay? So following this GPI, the generalized policy iteration, so which is this, right? We consider transition from state action pair to state action pair, and then the values of state action pairs. So if you look at here, we put this, the TD learning. Previously, you need to notice that here all the values become Q, okay? Q, 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 Q instead of V. Previously, if you look at the previous, we have, or we don't have. So look at this. This is the value V, state value function. Now we move all V become Q, which is action value function. Means we want to update the action. You see this value become Q, okay? With the action, the quality of the action. So now we replace the V with the Q, the state of action value, okay? So then we update the previous action value. So in this way, we call it SARSA method, because it uses SARST. We are in the current state, we give an action, then we get the reward in the next state, we move to the new state, we select an action again. So we repeat this process to update the policy. So the process is straightforward. Yeah, so we just use if you compare the previous one is the policy TD0 prediction, this time the policy TD control, okay? So we update the action value function. If you look at detail, so actually you also need to be you need to notice that we don't specify those whether it's epsilon greedy or epsilon soft. It can be epsilon greedy, it can be epsilon soft. So in this case, just for example, we can use epsilon greedy to choose an action from S. So when we choose an action, it can be the epsilon greedy, can be epsilon soft. So choose A from S using policy divided from Q. Okay, so then we just take an action, observe the R S prime, and choose A prime from S prime using policy divide from Q. So now we choose action again from the Q. Then with this information, we can update. So this is it also follows the pattern of TD, right? You have the current state, then you choose an action, you move to the next state, then from the next state, you update the previous policy. Okay, then we just update since we are moving to the new state, we just updated the current state S prime to the S A prime to A. Okay. So let's look at the example. We use the epsilon greedy SARSA for windy grid world problem. What is a windy grid world? So different from the previous setting. So now we have this grid world. We have starting point. Our goal is to reach this point. So the difference is that there is a strong wind from this side to the upward. So it will blow to here. Then the meaning of this wind is that there's a number 0, 1, 2, means that once you reach some particular point, state, if you move one step, for example, if you in this state, if I move one step, I move to the right. So because the current state of wind is 1, actually I'm going to move upward one step to here. Okay, this is called, what is the meaning of this 1? If it's 2, for example, if I'm staying here and I move to the right here, actually I'm gonna move to this place because the strength of the wind is 2. Where even though I move to here, the wind blow me to here. The two states, 2 cells. So if another setting is that if we stay on the boundary area, there's no effect of this wind. So we will just, if we move to the right, we'll stay here. It will not be blown out of this green wall. We just stay here. So the wind strength will not affect the location. Okay, this is the setting for this wind degree. So we have this epsilon 0.1, alpha equals 0.5. Epsilon is the epsilon greedy policy. How many percentage we're gonna choose the non-greedy actions. Then alpha equals 0.5 is the step size. The reward is -1. So each time when you move 1 step, you get -1. So now with the purpose is that what is the optimal path for us to reach this goal from starting point. So we can run this epsilon greedy salsa for this algorithm. If, for example, here from right-hand side, you see this. So there is an episode and also time step. If you run this by varying this time step and the episode, eventually when you reach to 7,000 to 8,000 the time step, we got our optimal path in this way. So means that actually, if you start here, it will just give you the instruction you need to move to the right, because at this point there's a wind. Even you move to the right, actually you are here. Move to here, you are in the next location. Move to here, actually you are moving to here. But once you reach the wall here, the strong wind has no effect for you. Then you can just keep moving. Because this place there's no wind, 0, you can move to back, move to here. Then eventually you moved 1 step, actually you reach your goal. Okay, this is the optimal path. It means that the reward, because you will spend the minimal steps to reach your goal. Because each step you will have a -1 reward, right? Means that this path compared to all other possibilities is the minimal, the expense to reach the goal. So also we need to note that Monte Carlo methods may not be used here because Monte Carlo method need to update the state when one episode is in the terminal state, it can update. But in here, actually, is sometimes it can have an infinite episode. Why? Assuming that you are staying here, then you move to downward. Because of this wind, you move back again. You move downward again, you move back again. So actually you will have infinite episode. You will never leave this place. You are fighting with this wind. Yeah. Okay. So this is about the SASAR algorithm. Now we move to a new method, which is Q-learning. Q-learning actually quite famous learning algorithm. Actually, you will see a lot of places to use this Q-learning because it is off policy, and it also the TD. It update the control, update the policy based on the TD. So it's like actually it has a lot of features here. It's off policy means that it will update the policy better, faster, and TD is online, dynamic update the state, means it'll converge faster, and also control is where do the prediction and update the policy faster. So means that generally the Q-learning is faster than others approaches in most cases. So actually the idea here is simple. We just, instead of looking at here, instead of if you look at the salsa, when we try to update the action value function, we use the next state action value, right? So, but this action taken is based on the policy pi. Instead of using this policy pi, we just select the greedy policy. We just use the select the action, like maximize the next state, instead of using the current policy to get the action value function. So that's why it's called off policy, right? Because actually we are not relying on the target policy. We are using a policy. Actually, we are not specifying a particular name for this policy. It's behavior policy, but actually this policy just use the greedy action based on the current action value. Okay, so that's why we call it off policy TD control. Then we just use the select the action with that maximize the next state action value. So yeah, so the explanation for this algorithm is that this learn action value Q directly approximates Q star, which is the optimal policy from the pi. Okay, so here. So even though we are using Q here, but actually the value of Q has nothing to do with the target policy pi, because the action we are selecting here is greedy. It's not based on the policy. We just based on the state value, okay? The optimal action value function, so which is independent of policy being followed. So sometimes actually there's one question in the textbook. It asks why this Q-learning is off policy, because that's the reason I'm explaining, because the action we are taking is not from pi. The action we are taking is from the next state, the greedy action. Okay. So yeah, others are just simple. So we just put a little bit different. So for this Q-learning, and because of policy TD control, right? So for each step, others the initialization setting are the same. So choose A from S using policy divided from the Q, epsilon greedy. Now take action A, observe R S prime. So from here, we choose action. Then eventually when we update the quality, the state action value function, so we are using the greedy action instead of the action from the policy. This is one major difference here. So this is Q-learning. There's another method. So we are looking at the different variants of this TD learning, okay? We call it expected salsa. So from the Q-learning, you see here, the Q-learning we use replace the greedy action with all the possible actions in the current policy. Actually, it's now for this greedy action, we now move back to the Bayes-Man equation. Instead of consider only greedy action, we consider all the possibilities of the surrounding states, right? So all the surrounding actions. Now we just use this. We try to get the update from here. Based on the policy pi, the action value function, then we sum them together, get all the possibility of action. So it's performs slightly better than the salsa generally, but with a higher computation because we have this summation operation. Okay, you need to consider more possibilities, more branches. So so far we looked at these multiple algorithms, the Q-learning, SARSA, Q-learning, expected SARSA. So actually they have one issue. We call it maximization bias. Okay, the issue here is that because we always the maximum overestimate value is used as an estimate of the maximum value, which leads to a significant positive bias. So if you look at here, Q-learning uses this greedy policy, is a max operation, right? Epsilon greedy SARSA also uses the greedy policy, max operation. So if you look at because here the choose A prime from S prime using policy epsilon greedy. So it's part of the greedy method. So then it caused some, so since we are having this, we are always using this max operation, greedy policy. So sometimes, even though the true value is 0, but actually because our estimate is fluctuate up and sometimes positive, sometimes negative, but we are always choosing the positive one. So which causes the bias to the true value of 0. So we call this maximization bias. Maybe a little bit like abstract. So let's look at the example. So this example, so if you look at this diagram, so we have the simplified Markov decision process. If it's a reward process or decision process, we have so we have this state A and B. You can either move to left or right. So the reward are 0. Then we are always starting from A. But after B, there's a terminal state. There are a lot of many passes with the reward following the normal distribution with the mean minus 0.1 and the standard deviation 1. So if you look at this, the shape of the probability distribution of this reward is this way. So the mean is minus 0.1, which is located here. And if you look at here, so if you draw a sample from this distribution, you have very higher chance to get the positive value from 0, right? So you will get very higher probability to get positive value. Means that actually this reward from B to the terminal state, many of them will have a positive reward instead of the 0 and 0. But if we are using the Q-learning, so you see, because if you use Q-learning, eventually we are updating the state, the action value based on this mean. Actually, eventually it's the mean, right? If we update again, it convert to the mean minus 0.1, which is. But through the process, there are a lot of positive values happens between B to the terminal state. In this case, from B to the terminal state, a lot of positive values. In that case, we are choosing. So ideally, we should not choose this part. We need to choose right direction instead of this left, because the reward here is minus 0.1. Obviously, it's smaller than the here, right? We need to get higher reward instead of the lower reward. The better solution, we always need to choose the right instead of left. But because so there's a lot of positive values here. So when you calculate those TD, many times the B is positive, and so you probably will choose B to the terminal state because it's the greedy way, the maximum way. If you run this simulation with Q-learning, so we have these episodes and the percentage of left action from A. So you remember left action is less desired action, because if you run it enough, the average is minus 0.1. The reward is lower than the right. So we need to get higher reward 0 is better than the minus 0.1, right? So, but because of this bias, the Q-learning actually will try left a lot at the beginning because it has a lot of positive rewards. It doesn't know the mean, the mean value is the minus 0.1. Then after some time, it gradually decreases to a better solution, better policy. So to solve this problem, we introduce so-called double Q-learning. So we will look at in the next page. Yeah. Any questions for this issue? Understand? Maximization bias. So simplify, you just look at here, this diagram. So because if you run the simulation enough, from this side, the return for this terminal state will be minus 0.1, right? Because eventually, if you run enough time, it will reach to the mean value. But from the right-hand side, whenever you run, it's always 0. So 0 must be better than the minus 0.1, right? So the right-hand side should be the better choice instead of the left. But since this is a distribution, among those distributions, there are many positive and negative rewards. So if those positive rewards are considered, because we always consider the maximum greedy action, if those reward is considered, then the B value will become positive in some time. Then compared to the right-hand side, then B become positive, then obviously A will choose to left direction, right? That is the bias we are talking about here. Then it's also verified by this Q-learning. Sometimes it happens. To solve this issue, we can do so-called double learning. If we divided the play into two sets, use them to learn two independent estimates. We call them Q1A or Q2A. So what we do is actually it's a little bit close. Looks like in the neural network, sometimes we use the skip, right? We can skip the connection and then move to the one we calculate again. Then sometimes we give some probability, it can skip or it can calculate. So similar concept here, double learning, is that we have this Q1, Q2, then we give some probability. They can use either Q1 to update Q2 or Q2 update Q1. This is sometimes maybe Q1 keep updating Q2, sometimes Q2 update Q1. So the two action value updates mutually, okay? They have some probability to update. We call this double learning. So in the algorithm design, we do this way. With some probability, like 50% probability, we use Q2 to update Q1. With another 50% probability, we use Q1 to update Q2. So mutually update. So sometimes depends on the probability, right? Sometimes we just keep using this. Sometimes we just keep using this to update. In this way, mutually update. It's like to avoid jump into a particular state, right? For example, if you consider this case, previous case, if we meet some positive value, we greedily select the positive value, then the left action will be selected, because it's greedy, it's maximum operation. But as it has 50% probability that left action will not be selected because we will use another Q2 to update the policy, right? So it's like we reduced the possibility of choosing the to jump to fall into this trap, this maximization trap. Then if we look at this the diagram, actually initially if you look at it carefully, initially actually there's an upside down. They have some probability. So but to select those less desired action left, right? But once it realize that action is not good, then you actually decrease quickly. So to select instead of selecting those left action. This is double Q-learning, and yeah, this double Q-learning has been used a lot in different problems because practically it has good performance to avoid different kind of issues. Okay, summary. So far we have learned this TD. Like we have a TD method, different TD method, right? We first do the state value update. So if you look at, I listed all the variants of the TD method here. If you initially the concept or the idea of TD is that we just use the next state to update the previous state, right? The next state update the previous state, which is R+1 plus this the gamma v st next state value. So this is the basic way TD0. We call it TD0 method. Now we want to not only update the state, we also want to control the policy, update the policy. Now we move to the Q. We use SARSA to control the policy. Actually, SARSA is the same concept of the TD0. Instead, but it's just the difference is the TD0 update the state value. SARSA updates the action value Q. Okay. After that, we so even though we are using this, so this is on policy, SARSA is the on policy method. So we can, instead of using the policy, the action from the policy, we can just select the greedy action based on the next action value instead of following the policy. Then then it brings us Q-learning. The Q-learning uses greedy action to control instead of the action from the policy. So that's why we call Q-learning is the off-policy learning. Then we move to another step. If we consider all the possible actions in the next state, then we use the Behrman equation. We just sum all the possible actions from the positive pi. Then we update the previous call it the action, the policy, the action value. Then we call it expected SARSA. But there's some maximization bias. Then we design this double Q-learning. We use two action value functions to mutually update each other, then to avoid jumping to the maximization, the bias. So this is the whole knowledge of the TD. And so any questions? Mm-hmm. Yeah. So because when the Q-learning was designed, so actually you need to consider the computation cost because the Q-learning has been designed in 1989. Yeah, 1989. The Q-learning, the first version of Q-learning has been proposed. At the time, the computation power is not that strong. It's low. So if you run like triple, I mean, obviously you can run unlearning, like, but maybe the speed will become very slow. But I don't know if for now, if people try multiple Q-learning. Yeah, but because the computation power is much higher than back to the like 20, 30 years ago. Yeah. Yeah, but since the performance we are looking at here is already improved, but I would maybe it has improvement, but may not that significant. Maybe very close, very little improvement. If you have triple or multiple Q-learning, maybe a little bit improved, but maybe very close. The improvement is very small. Yeah. Okay. Any other questions? Okay. Thank you for your attention. And we conclude this lecture today. And see you next week.